Good morning, everyone. Welcome back to the seventh lecture of the workshop of PWF, Expanding Horizons in Physics in Sudan, the second edition. The density functional theory methods and applications. Today's lecture will be given by our distinguished speaker, Dr. Iurii Timrov, a senior researcher scientist at the Laboratory for Material Simulations at Bolshoi Institute, Psi. Also, he is a member of the planning committee of the African School on Electronic Structure Methods and Applications. He has an extensive experience in the field of computational material science. Today, he will be talking about advanced exchange correlation functionals. Thank you very much, Dr. Iurii, and it's a pleasure to have you. Please, you can share your slides now.
Thank you for the kind introduction.
Okay. I will stop sharing.
Okay. All right. So, good morning, everyone. It's really my great pleasure to be part of this school. And today we will be discussing about the DFT plus U method. Anybody of you familiar with the DFT plus U? Okay, silence means probably not, which is probably would be interesting for you to learn what it is, because it's quite popular method and very useful. It's simple, but also very powerful. So I hope you will like this method. So yeah, let's continue. Let me start first of all with a brief introduction about the institute where I'm working. Apologies. So I work in the Paul Scherrer Institute in Switzerland, in the center of Europe. So this institute is named after the Swiss nuclear physicist Paul Scherrer. And this photo shows you the institute is divided by the river in two parts. Actually, historically, there were two institutes, one on the left side of the river and another on the right side of the river. And they are called actually East and West. So in 1988, these two institutes were merged into one. So Swiss Federal Institute for Reactor Research, that was created in 1960. And the second one is Swiss Institute for Nuclear Research in 1968. But then they were merged and called Paul Scherrer Institute. So as you see, originally the focus of the institute was on reactor research and nuclear research, but nowadays it's a portfolio of different topics, not only related to reactor research and nuclear, but much more, including condensed matter physics, chemistry, biology, radiotherapy, and so on. And it's located in the north of Switzerland, close to Zurich, close to the border with Germany. So I invite you to come and visit us sometime in the future if you have the opportunity. Institute is composed of many state-of-the-art facilities. So they are highlighted here. The most recent one is the so-called Swiss free electron laser, Swiss FEL. It's shown here, it's in the forest. It's actually under the ground, so you don't see it. I visited it once and it's really, really impressive. It's just incredible what engineers can do nowadays. And then there are other facilities, including Swiss Light Source, this circular building. It was also recently upgraded. It's very, very state-of-the-art. And then there are others like Swiss muon source, Swiss neutron source, where experimentalists do experiments with muons and neutrons. But also there is proton therapy, where there are treatments of patients with cancer and other problems. But also there are high precision particle physics, radiotherapy, hot lab, and energy system integration. And PSI is divided in several centers. If we go from the top clockwise, we see there is PSI Center for Neutron and Muon Sciences, but also PSI Center for Nuclear Engineering and Sciences. Also, there is a center focusing on energy and environmental sciences, photon science, scientific computing theory and data. Apologies. And I am working in this Center of Scientific Computing Theory and Data. But there is also accelerator science and engineering, corporate services, and life sciences. So you see, it's very, very broad. And in particular, if we focus on the Center of Scientific Computing Theory and Data, it's also divided in 4 laboratories. So there is laboratory for simulation and modeling, then theoretical computation and computational physics. Then there is science, IT, infrastructure and services, and laboratory for material simulations. I am working in the laboratory for material simulations. So a few words about our laboratory. So this is the laboratory head, Professor Nicola Marzari. The mission of the laboratory is to develop, integrate, and disseminate a PSI community, and more broadly, new computational capabilities that are required to understand, predict, but also to characterize materials that are studied at PSI using different particles such as photons, neutrons, muons, and electrons. And our laboratory is divided in turn in different groups. There are 5 people. So myself, the first, I'm a tenure track scientist. I have a small group composed of 6 people, and we are working mostly on batteries, such as lithium-ion batteries and sodium-ion batteries. Also, we work a lot on magnetic materials. We work a lot on methodological and theoretical developments, including DFT plus U, and computational spectroscopies. So that's why I will be talking today about DFT plus U, because I worked on this method for more than 10 years. And then there is another colleague, Nicola Colonna, working on materials modeling, ARPES, which is angle resolved photoemission spectroscopy, and other topics. And then there are other group leaders, such as Giovanni Pizzi, Michael Schuller, and Matthias Krak. They're working on other topics that I will not discuss in detail, but you can see them on the slide. In my group, we have 6 talented people, 2 PhD students, Valentina Sanella and Stefan Sharon. They are working on batteries. Maria Andolfato and Romana Botti, they work on magnetic materials, magnons, and magnetism. And Noor, she's actually from Egypt, and she did her semester project with us. She already finished it, actually. And Moritz Gubler was a postdoctoral researcher working on methodological developments. And he actually also already left the group, but there are new members coming in the near future. So that was a brief introduction about the institute, where I work and what we do. And now let's go smoothly to physics and the topic of today's lectures. So in the previous days, you learned a lot of material about density functional theory and many other topics presented by my colleagues. And I have the privilege to continue today with a bit more advanced topics, such as DFT plus U and others. So let's start with the DFT. Ideally, we would like to solve the Schrödinger equation, H psi equals E psi. And this equation was actually invented in Switzerland, where I am now, when Erwin Schrödinger was on vacation in December in Alps skiing. It was almost 100, actually more than 100 years ago. And actually, when he was on vacation, he came up with this brilliant idea of inventing this quantum mechanical equation. He said, okay, great, we have this equation, but the problem, it's too complicated to solve it in practice. So it's very beautiful, elegant, and compact, but it's very difficult to solve for real materials. So we need to do something about it. And these 2 individuals, they got the Nobel Prize in Chemistry in 1998, exactly to finding solution to this problem. So basically, they worked a lot on numerical methods. So John Popple, he worked in chemistry, and Walter Kohn mostly in physics. And so Walter Kohn with colleagues developed density function theory. You already heard about it. And John Popple, he developed different numerical methods for quantum chemistry. And altogether, thanks to these two professors, there is a big breakthrough in chemistry, in physics, and material science for the development of numerical methods that allow us to approximate and solve Schrödinger equation for real materials and molecules. And that's why they got the Nobel Prize in chemistry. Even though Walter Kohn is a physicist, but he got the Nobel Prize in chemistry. And this is a table showing most cited papers in the history of American Chemical Society, starting from 1893. So there are 20 papers, and they are the most cited papers in APS. And in red, I highlight those papers that are related to numerical methods, such as DFT and GGA, such as Generalized Gradient Approximation, and other, like ultrasoft pseudopotentials and so on. So this is just to show you how important it is what we are learning in this school. It's really, really important, powerful, and it's the most cited papers. It means people use it a lot. So 18 out of 20 papers are related to numerical methods. Another example, if we take this interesting paper published in Nature Journal in October 2014, is the most prestigious journal, one of the most prestigious journals in the community. And here there was an interesting experiment. If you take all papers published in different sciences, such as medical, engineering, literature, physics, chemistry, biology, and so on, and you take only one page of every paper and stack them, and then you zoom at the top. So you're curious, what is actually the most cited papers? Top 100. And you will see that 12 out of top 100 papers are actually related to density functional theory. This is again showing you how important it is. And you already learned in this school about density functional theory, but I would like just to remind you briefly before we move to more sophisticated topics. What is DFT? Very simple in schematic way without too many equations. So what is DFT? I mean, what does it do in practice? So on the left is the real quantum mechanical problem. We have electrons represented by dots, and these red arrows indicate that they are interacting. So we have a complicated problem to solve. We have many electrons, and all of them are interacting and moving around. So how to describe this quantum mechanical problem? And in quantum mechanics, we work with the wave function, quantum mechanical wave function psi, that depends on the position of all electrons. So R1 is the position of first electron, R1 is the vector in 3 dimensions, so that it's x, y, z. Then R2 is the position of second electron, x, y, z, and so on until the very last electron, which we call n, capital N, and also has x, y, z components. So we are working with 3 multiplied by n number of variables. So 3 because of 3 dimensions multiplied by n number of particles. So we need to solve the Schrödinger equation for a system composed of 3 multiplied by n number of electrons that are interacting. This is too complex. We don't know how to do that in practice exactly. Maybe with quantum computers, one day we will be able to solve it, but for the moment, we need to do something, do some simplifications or approximations. And this is exactly where DFT comes into play. Thanks to Walter Kohn, he proposed to introduce a new object, density, charge density n, that depends on only 3 coordinates, x, y, z, which we write as r bold. So it's a vector. So this is just a function that depends on 3 variables. And this is much simpler than working with the psi, which is the function of 3 multiplied by n variables. So if, let's say, n is 1,000, so 1,000 electrons multiplied by 3, it's 3,000 variables. And instead, in density, we have just 3 variables. So of course, 3 versus 3,000 is a big deal, right? So now we replace the problem of many body wave function by just a density, which is a simple function. And this density is obtained by integrating the square modulus of the wave function over all variables from R2 to Rn, except one, R. This is exactly the density at that point, R. And moreover, we replace the true interacting system of electrons moving in some potential by an auxiliary system. So now we draw the electrons in orange just to indicate that they are fictitious electrons, non-interacting, because you see there are no red arrows between them, they don't interact. However, the price to pay is that they are moving now in some kind of effective potential, represented by this dashed parabolic-like potential, for simplicity, and it's called Kohn-Sham potential. So what we do here, we replace a many-body electronic system that are interacting and moving in external potential by an auxiliary system of non-interacting electrons moving in an effective potential, which is called Kohn-Sham potential. So that's the whole idea of density functional theory, simply speaking. More rigorous explanation was given in previous days by my colleagues, but this is just a simple, let's say, summary. And another slide, just to refresh your memory from previous days. In density function theory, what we have to do is to solve the so-called Kohn-Sham equation that you heard a lot about. And it's written here. So we have in these brackets, we have kinetic term minus h bar squared divided by 2m0, where m0 is the mass of an electron and the gradient square or Laplacian, plus the potential, Kohn-Sham potential. And this is the eigenvalue problem where epsilon are eigenvalues and psi are eigenvectors. So we call them epsilon, we call Kohn-Sham energies, and phi we call Kohn-Sham wave functions. So we want to solve this equation for any material that we study. And here the Kohn-Sham potential is composed of 3 potentials: Hartree potential, exchange correlation potential, and external potential. Hartree potential has exact form. It's E squared, the charge of an electron to the power of 2, and we integrate the density divided by R minus R prime, the Coulomb potential. So this is the Hartree potential, it's exact and easy. External potential, it's also given. And what is not known is the exchange and correlation part. So this exchange correlation potential is defined as the variational derivative of the exchange correlation energy with respect to the density. And this is what we don't know. So the DFT approach doesn't tell you what is the exchange correlation energy. There are Hohenberg-Kohn theorems, 2 of them, and they say that there should exist exact exchange correlation functional, but it doesn't tell you what it is because they don't know what it is. And nobody knows what it is. So that's why we try to approximate it. And there are many exchange correlation functionals that are approximate, but try to get as close as possible to the exact one, which we don't know. And Feynman called this exchange correlation part the stupidity energy because we don't know what it is. And historically, the most popular exchange correlation functionals are local density approximation, or in short, LDA, and generalized gradient approximation, in short, GGA. In LDA, it's very simple. We just assume we start with the homogeneous electron gas, and we assume that the density is a local object, and the functional is also local. depends only one position in space. Instead, in generalized gradient approximation, we just do one step forward. Instead of just working with the density, we also work with the gradient of the density, hoping that it gives us more information how the density changes, and it should improve the results. And in fact, it improves for many properties, but sometimes it's interesting that LDA could be even more accurate than GGA. And in GGA, there are many, many ways how you can design the exchange correlation functional. There is no one unique way. There are many ways how to do it, how you can parameterize it. And that's why there are really a lot of GGA functionals. And most popular ones are PBE and PBE Sol. So PBE was introduced first in the 90s for atoms and molecules, but people also use it for solids. But then later it was reparameterized for solids specifically, and that's why there is PBE solids, PBE Sol. But there are also many other GGA functionals. So these functionals are very nice, simple, and they have a lot of success stories, but they have also serious problems, such as self-interaction errors and lack of non-locality. So self-interaction errors, the consequences are D and F electrons are over-delocalized. So in reality, D and F electrons are localized in space. But due to these approximations, they are over-delocalized. This will be the topic of today's lecture. I will talk more about this. Another consequence, incorrect description of charge transfer. When there is a charge transfer from one part of the molecule to another part of the molecule, for example. Third one is incorrect energetics of chemical reactions. And fourth, underestimation of the band gaps, probably one of the most famous problems. And there are others problems. And also the lack of non-locality. There are consequences such as incorrect description of weak long-range interactions, so-called van der Waals interactions. If we have time, I can also talk about van der Waals functionals today. Also inadequate description of bond breaking and formation, and no Rydberg series and others. And so there are more advanced functionals to tackle some of these problems. There are many advanced functionals, but I would like to highlight four most popular families. The first one is the Hubbard functionals, such as DFT plus U, DFT plus U plus V. We'll talk a lot about this today. There are also hybrid functionals, such as B3lib, PB0, HSE06, and so on. Then the third family are meta-GGA functionals, such as TPSS, SCAN, R2SCAN, and van der Waals functionals, such as DFTD, DFTD3, TS, and RVV10. And starting from next slide, I will start discussing a lot about DFT plus U. But before we move forward, I would like to take a little pause and ask if you have any questions, if I go too fast or too slow, because this is quite complicated. This school covers a lot of topics from very fundamentals to advanced. So today we're talking about very complicated topics and advanced. So I just would like to check on you if you're following me or if you have any questions. Don't be shy, please unmute yourself and ask anything you want.
For the participants, you can also write your question in the chat and I will read it.
Yes, exactly. Okay, so no questions? Okay,
Hello, can I ask question?
please.
I just want to know why the exchange correlation is not known or cannot solve.
Okay. Thank you for the question. So when Hornberg and Kohn introduced their theorems. They derived this beautiful theory, like density functional theory. It's a functional theory because we work with functionals. However, I mean, they said, yes, you can replace this complicated problem by a simple problem. So basically, all these complicated effects of many-body electronic interactions are somehow compressed into this one object, which is exchange correlation functional. So somehow we cannot have free lunch. It's like the problem is still there. We just compressed it into the exchange correlation functional. So exchange correlation functional, what it is? These are quantum mechanical interactions, exchange and correlation, basically describing how electrons interact. So you see there are many electrons and they interact. And there are electrostatic interaction like Hartree potential, so there is electrostatics, but also there are quantum mechanical interactions such as exchange and correlation between electrons for many body systems. So it's very complicated and it's all kind of compressed into one object, and we say, okay, we don't know what it is, but it's kind of should describe that complex interactions. So that's why we don't know it. It's like, yeah, you have a problem, but you just kind of reformulate it in a different way such that you put all what you don't know into one object, but then you say, okay, I don't know what it is. I mean, that's how kind of it works. I don't know if it was clear enough or not. Because in the previous days you heard about density functional theory, and they should have introduced Hoenger-Kohn theorems and mentioned about exchange correlation functionals. But yeah, it's something that we don't know.
Yes, I get your point. Thank you.
Welcome. If we knew the exact exchange correlation functional, that would be very beautiful, because we can describe materials very, very accurately, like they are in nature. Unfortunately, we don't know what is the exact exchange correlation functional, so we need to approximate it. And people try to do as best as they can to try to kind of figure out what is the exact exchange correlation function. If you happen to figure out what it is, you will get the Nobel Prize. I think. I don't know in physics or chemistry, but you can get the Nobel Prize, I think. But if we knew the exact one, that would be very nice. We would solve a lot of problems. Any other question? Okay, so I think we can move on. Let's start discussing about DFT plus U. So what is DFT plus U, and when do we need it? So, and what is this mysterious U? So let's try to understand it. So first of all, when do we need DFT plus U? This is the periodic table of elements, and any of you knows when do we need DFT plus U? Maybe you heard about this method a little bit. So you can suggest what are the elements for which we might need DFT plus U. So we need them, we need DFT plus U for, sorry, there is a comment. No, okay. So we need DFT plus U when we work with transition metal elements, such as the third row. So actually this row from titanium to zinc. I mean, actually for zinc, we don't really use it, but this row, next row. So this row is 3D, next row 4D electrons, 5D, and so on. So whenever we have materials that contain these elements, transition metal elements containing D electrons, we need DFT plus U in most cases. Also, in materials that contain rare earth elements, such as lanthanides and actinides. So these elements that contain F electrons, such as 4F and 5F electrons. They're also very localized in space, so we need plus U correction. So whenever we have rare earth, so rare earth and transition metal elements, we need plus U. Because transition metals, they contain d electrons, and rare earth contain f electrons, but also d electrons. So basically, whenever we have d and f electrons, because they're very localized in space. And these materials, they have technological importance. So transition metal elements and transition metal compounds and rare earth compounds. So these materials, they're used for many applications, such as batteries and for electric cars, magnets for generators, and photocatalysis, let's say titanium dioxide, spintronic devices, inorganic perovskite solar cells, and so on. So there are many, many applications. So theoretically speaking, if we want to model these materials, we often need DFT plus U. And now let me explain a little bit what's the problem. Let's start with this cartoon. And this is a simplistic picture of bulk iron. So here I represent by blue, these are the iron atoms. And every iron atom, it has electrons. And we can divide these electrons in two groups. First group would be called core electrons, because they are close to the core and they're very bound to the electron. You can see there are these inside this purple atom, we have electrons that are orbiting around a nuclei. So these are called core electrons, such as 1s, 2s, 2p, 3s, 3p, and so on. So they're the closest to the nucleus, and they're very bound. They stay close to the nucleus. They don't go away. But then there are also outer electrons, such as 3d, 4s. So they are far away from the nucleus, and those electrons are external electrons, and they actually can be floating around. So you see, while core electrons are orbiting around the nucleus, the external electrons, they're actually flying around. They don't belong to one particular atom. They actually don't belong to any atom. They're called delocalized or itinerant electrons, and they are flying around. They are kind of free to move around. So this is for the bulk iron, which is metallic. And this is because there are electrons that are flying around. Now, if we take iron and combine it with oxygen, so now we have bulk iron oxide, the picture is completely different. So now we don't have those flying electrons. Now they became localized. You see now this external electron, they're orbiting around iron atoms. So they became localized. And this material is actually insulator. So there is a band gap, it's insulator. And electrons are bound to nuclei, so they are localized. So this is very interesting, because if you take iron, it's metallic, and there are itinerant delocalized 3D electrons. But if we combine it with oxygen, the picture changes a lot, becomes insulating, and electrons are localized. So for us, computational people, modeling these two materials, iron and iron oxide, it's two different problems. Because iron we can model with simple LDA or GGA functional without any Hubbard-U correction. But iron oxide, it's insulating, and there are localized electrons. Here we need a plus U correction. It's very interesting, no? Like if you just pure iron, no need of Hubbard-U. If you put oxygen and mix it with iron, you need Hubbard-U. That's interesting. And actually, coming back from that very simple cartoon to the real materials, we also have the same observation, like in iron oxide, when we have localized electrons. So here we have example of a battery compound, lithium 0.5, iron, phosphorus 0.4. So we still have iron and oxygen, but also we have phosphorus and lithium. And this material is used for batteries. And on the left, I show you the correct picture. We have this unit cell of this material. So lithium atoms are in the corners of this unit cell. Then we have iron atoms, big red balls. Then we have oxygen atoms are small red balls. And then we have phosphorus are yellow atoms. And in real life, in this material, iron exists in two oxidation states, 2+ and 3+. So we will talk about it in a moment, what are those oxidation states. But if you use approximate functionals such as LDA or GGA, you find incorrect description of this material, because instead of finding mixed valence case of iron 3+ and 2+, you find something on average 2.5+. So now let's discuss a little bit what is this 2.5+, 3+, and 2+. So these are called oxidation states. Any of you knows what is the oxidation state? No? Okay, then let me explain what is oxidation state. So in iron 2+, it means that we take away 2 electrons from neutral iron atom. And iron 2+ would correspond to 3d6. So the 3d shell has 6 electrons. So iron 2+, it means that we removed 2 electrons, and those 2 electrons were sitting in 4s. There was, in the neutral iron atom, there is 3d6, 4s2. And when we have oxidation state 2+, we took 2 electrons from 4s. So 4s shell is fully empty, but the 3d shell still has 6 electrons. Now, if we increase the oxidation state from 2+ to 3+, it means we remove 3 electrons. So we still take 2 electrons from 4s, so 4s is empty, but we take also 1 electron out from 3d shell. So instead of 6 electrons in the 3d shell, we have 5 electrons. And schematically, this can be represented like this. In 3d6, we have 5 electrons spin up and 1 electron spin down. So these are the levels, 3 T2G levels and 2 EG levels in 3D shell. So we have 5 up electrons and 1 down electron. And in 3+ iron, we have only 5 up electrons because we took 1 electron out. So this spin down electron was taken away. And oxidation state basically describes how many electrons belong to the atom. And it's indicated by this way, like 2+, 3+, 4+, 5+, and so on. It basically tells you how many electrons are taken away from the neutral atom. And coming back to our example, on the left, we have iron 2+ and 3+. It means in iron 2+, we have 3d6 configuration, and in iron 3+, we have 3d5 configuration. So you see that the iron 3+ has 1 electron more than iron 2+. So you see there is non-equal distribution of electrons. Instead, if we try to model this material, we find that all irons have the same amount of electron, on average 2.5+. Because if you take 2 plus 3 divided by 2, 5, it means 5 divided by 2, which is 2.5. Because on the right, we are not able to localize electron on one iron and not on the other iron. So this is related to the previous cartoon. You see, we want that electrons, let's say, localize on this iron, but not on the left iron. So in this case, they're all identical, but imagine there are 2 types of iron. One has 1 electron more, another 1 electron less. So in real life, we have this mixed compound, mixed valence compound. But if you try to use LDA, GGA, you will not be able to describe this material. That's exactly where the problem is. And that's why we need the plus U correction that can help us to describe it as 2+ and 3+. It's basically what we're trying to do is to control the localization of electrons and charge distribution in the system. And this is related to the so-called self-interaction error. So this problem of not being able to describe localization of electrons is related to the self-interaction error. Before I move forward, any questions about these concepts? Oxidation state, localization of electrons, anything unclear?
Yeah, clear.
Okay, thanks.
I think I have a question.
Yes, please.
Why are some materials are localized and other material delocalized? Why? What is it?
Yeah, it's a very good question. It's just the nature. I mean, let's say if you take iron, it's metallic and electrons are floating. But whenever you put oxygen, because now we have two types of atoms like iron and oxygen, and they are interacting, and this somehow changes the electronic properties of the material, and electrons become localized. So yeah, I mean, basically in nature we have many materials. Some of them are metallic, some of them are insulating or semiconducting. Yeah, that's the beauty of nature. I mean, if we come back to the periodic table, we have so many elements. Look how many of them. And if you start combining them together, there's so many possibilities that you can build materials. Let's say, in this case, we take iron and combine it with oxygen. That's one material. You can take instead nickel and combine with oxygen. Or you can take psyllium, let's say gallium arsenide, semiconductor, or there's so many materials. And some of them are metallic, some of them are insulating, semiconducting, some of them become superconducting, some are non-magnetic, some are magnetic, and so on and so forth. So basically, there are so many possibilities of materials, and they are different from each other, right? If they were all the same, that would be boring and we wouldn't be living in this world, but all of them have different properties and in terms of magnetism, electronic structure, and spectroscopical properties. And it's interesting because when you start combining together different elements with different electrons, they start interacting, hybridizing, and as a consequence, it can be either metallic, it could be insulating. Yeah, that's very interesting. That's how materials work, and we just try to describe it theoretically with quantum mechanics to understand why it's metallic, why it's insulating. That's exactly what we're trying to do. But that's the beauty of nature, that we have different types of materials. But for us theoreticians, we don't have one method that works beautiful for everything, unfortunately. If we had the exact exchange correlation functional, we would be able to describe all materials with this exact exchange correlation function if we knew it. Unfortunately, we don't know it. So that's why we design functionals specific for families of materials. Let's say the family of materials that contain transition metal and rare earth elements, we need this Hubbard-U correction. But in other materials, let's say when we have gallium arsenide and other semiconductors, we don't need Hubbard-U. I mean, we can use other methods, let's say hybrid functionals that are more appropriate for those materials. So this is the problem. We don't have the universal exchange correlation functional that all works for all. I mean, DFT and Walter Kohn claim, yes, there should be one that is universal. And if it was known, we would describe all materials with one functional. However, we don't know it, so we need to kind of tailor for each family of materials different functional because of their properties. Whether it's metallic or insulating, like delocalized electron or localized electrons. So we need to design different methods. That's not very nice, but that's how it works.
There is also a question on the chat. Why is DFT plus U required for the iron oxide?
Okay, so we need DFT plus U for iron oxide. because we deal with localized electrons. So you see in iron oxide, it's insulating, which means electrons are bound to iron, they're localized. And whenever we have localized electrons, we need DFT plus U, because the plus U correction allows you to describe the localization. I will tell you in the rest of the lecture how it works. So basically the plus U correction applied to D electrons allows you to localize them. So basically when we apply plus U, we localize electrons, because if you don't apply it, they will be delocalized. As a consequence, you will find the same metallic solution, which is not correct. So if you try to perform DFT calculation for iron oxide without Hubbard U, using just LDA or GGA, like here, if you use LDA GGA for iron oxide, you will get metallic solution, which is not correct because of self-interaction errors. This is exactly where we are going. Since in LDA GGA there is self-interaction error, these electrons that are in nature localized, they become unphysically delocalized. As a consequence, they become metallic, like here. But with plus U correction, we can fix that problem. This is exactly where we are heading. Okay, so probably we can move on. It's actually already the time for a break, I think, right?
Yes, if you want, we can take 5-minute break and we come back.
Okay, I think we can take a little pause to digest all this information before we move forward exactly to understand what is DFT plus U and why do we need it for iron oxide. This will be described in the rest of the lecture.
Okay, perfect.
Okay, so thank you. Please take a little break and we reconvene in 5 to maybe to 10 minutes maximum.
Okay.
Thank you. Okay, we are back.
Yes, we can continue directly.
Perfect. Before we continue, maybe there are some other questions. Okay, if not, then let's move on. Finally, to understand what is DFT plus U, I hope I intrigued you a little bit. So what's the problem, to summarize? So the first problem is this material that we try to describe, and we have this iron 2 plus and 3 plus that we're unable to describe with LDA and GGA because we get 2.5 plus. That's one problem. And also we wanted to understand why iron is metallic, we don't need Hubbard-U, but iron oxide is insulating and we need Hubbard-U. So let's try to understand why. So all this is actually connected to the so-called self-interaction error. So the name of this is already telling you there is kind of some self-interaction. Something is interacting with itself. So actually, self-interaction error arises because of the incomplete cancellation of self-Coulomb terms by the approximate exchange correlation energies. So what does this mean? So in the center of the slide, we see the Hartree potential. Let me connect to what I've shown you. So this is the Conchem equation, and we have Conchem potential, which has Hartree potential, exchange correlation, and external. So we have Hartree and exchange correlation. And what I'm saying is that there is kind of self-interaction because the Hartree potential is exact, while exchange correlation potential is not exact. It's approximate. And due to this approximation, there is a problem related also to Hartree potential. So what's the problem? So this is the Hartree potential. It's an integral of the total charge density divided by r minus r prime. So the Coulomb potential. So what is the thing here? The thing is that this is the total density, right? Hartree potential is the potential that we use for a fixed electron, right? Let's say we take one electron, and for that one electron, we are trying to solve Conchem equation, which depends on this potential, which depends on the total density, but total density includes that electron of interest. So what we are having basically is that when we're trying to solve the Conchem equation for an electron, we use this potential that depends on electron itself. So there is kind of self-interaction. Electron interacts with itself through the density. If we had exact functional, there would be no any problem because the exact functional would cure that kind of closed loop. Exact functional would not allow this self-interaction. It would compensate for it somehow. But since we don't know exact one, we approximate it. So there is no exact cancellation of that self-interaction. That's why there is this self-interaction present whenever we have approximate functional. Just to make a side note, if you use just one electron system, there are no many electrons, only one electron, and you use Hartree-Fock approach, there you don't have any problem. Because in Hartree-Fock method, I don't know if you were presented to the Hartree-Fock method in the previous days, but there is exact cancellation of self-interaction in Hartree-Fock for one electron, that specific case. But that is just one electron, who cares? In real materials, we have many electrons, and we use approximate functionals. And that's as a consequence, there is no cancellation of this self-interaction. And as a consequence of self-interaction, there are many, many bad consequences, such as shown here. There is over-delocalization of electrons, incorrect description of charge transfer, incorrect energetics of chemical reactions, underestimation of the band gap, and the list goes on and on and on and on. So it seems like, okay, there is little problem, but as a consequence of that problem, we have many, many problems. If we had the exact functional, it would be no problem. Life would be beautiful. But since we approximate it, we have many unpleasant problems that we need to deal with. And this is where DFT plus U can be helpful because it allows us to cure this. It's like an illness, and plus U is the medication to cure the illness. So probably there is a question. So I guess U is a special type of approximation. Yes, we can call it Hubbard functionals. It's kind of a approximation to the exchange correlation functional. Yes, we can say it that way, absolutely. So self-interaction is an illness. You go to the doctor and doctor tells you have this illness. It's called self-interaction error. And to treat this illness, I give you the medication, which is called Hubbard U correction. So that's how we can put it. So let's go back to our example before. We know already the system. On the left is the correct case, iron 2 plus, iron 3 plus. On the right is the incorrect case. So why do we have this incorrect case on the right? 2.5 plus oxidation state, which is incorrect. This is exactly rooted to the self-interaction error. Because of this unphysical self-interaction, when electron interacts with itself, which doesn't make any sense, we have a problem of the fact that iron 3D electrons that must be localized, they are actually delocalized and spread around the cell. So what we want in iron oxide, we want electron to be localized, so orbiting around one iron. But due to self-interaction, it doesn't want to do that. It actually delocalizes and behaves like this, like flies around. That was iron oxide, but even in this system, it's the same problem. We want electron to be one electron more on one iron and less on the other iron, but we are unable to describe this kind of mixed case. And this is because of self-interactions, which lead to the delocalization of 3D electrons. As a consequence, the wrong average oxidation state of 2.5 plus. And to make a step forward, this is actually related to the spurious quadratic energy change when we're adding or removing a fraction of an electron to iron. So this is a bit complicated. So let us take some time to understand what does it mean. So what we are talking about. So this self-interaction error and delocalization problem are actually connected to how energy behaves when we are adding electron to iron or removing electron from iron. So it's connected to this concept, which is very important for what follows. So what we're trying to say here. So here we're showing the energy as a function of a number of electrons. N is the number of electrons in the iron 3D shell. So we call it Hubbard manifold. So what the exact solution tells us, it must be piecewise linear. So let's say when we have n electrons, we have energy E of n. But if we have one electron less, n minus 1, so we have a different energy, E of n minus 1. And these two energies must be connected with a straight line. You see this green straight line connecting these two energy solutions. And if you take one electron more, like n plus 1, it will be still straight line. If you take two electrons out, so n minus 2, it would be still straight line. So these are called piecewise linear behavior. So it's not just linear, it's piecewise linear because there are pieces of lines that are connected. So the exact solution, if we had exact functional, the exact solution must be piecewise linear. So basically it tells you that when we're adding electron to iron or take out electron from iron, the energy must behave linearly. Okay. Instead, if you use approximate DFT with LDA, GGA, or any other approximate functional, because we don't know exact one, and since there are self-interaction errors, we don't have that green behavior, piecewise linear. Instead, we have something continuous, parabolic like this. And this is a consequence of self-interaction errors. And it's incorrect. So this cartoon on the left will be useful, very important for the next slides. So I just wanted to make a connection between this self-interaction error problem, delocalization, and this energy picture, which will be important for the next slides. So I'm sorry, it's a lot of concepts. They might be very new to you, a bit complicated to understand. So don't worry. It's the first time you hear about it, and you need time to think about, understand better. It's just the first time you see this. So don't be worried if you don't understand many things. You just keep listening. But later you can learn more, but this is like a first introduction to the topic, which is might be a bit complicated for you because it's advanced. Now we have clearly stated the problem, I hope. Now let's again go to DFT plus U and try to see how does it work, how this medication works. First, let's start with the history, why people and how they introduced DFT plus U. It's very interesting, actually, what happened. So Walter Kohn proposed his DFT in 60s, like between 64 and 65. And the main idea was explained at the beginning of the lecture. I don't want to repeat it again. You know it, the story. But interestingly, exactly the same period of time, from 1963 to 1967, another physicist, is a British-American physicist, John Hubbard. He proposed a different theoretical framework, which is known as the Hubbard model. He published several papers, probably 5 or 7, I don't remember, about this Hubbard model, its generalization, extension. But basically, he works with the model Hamiltonian. So H is the quantum mechanical Hamiltonian. And he works with the model system, two-dimensional lattice. You see it's two-dimensional grid. And he took some fictitious case. So imagine you have this two-dimensional lattice, and on every side of the lattice you have an atom. So every circle is an atom. And you have just one electron with spin up or spin down. If it's spin up, it's red arrow up. If it's spin down, it's blue arrow down. So every electron has a spin. It can be up or down. And I mean, when you have one atom on every side with specific spin, everybody is happy. But imagine that there is a hopping of an electron from one side to another. So it can happen that on one electron, you all of a sudden have two electrons, spin up and spin down. So now these two electrons are not happy. They repulse each other because they don't want to sit on the same side. It's like, imagine a bus, empty bus, right? Then people start coming in the bus, and you start take a seat, one seat, another person, another seat, third person, another seat. So everybody start taking 3 seats. But then at some point, 2 people might take the same seat, but they're unhappy because it's not comfortable. And for electrons, it's some similar analogy, and they start repelling each other. There is some Coulombic repulsion. They want to repel each other. And the strength of this repulsion, we can call it the Hubbard U constant. It's just a number in energy units, let's say electron volts. This tells you how strongly they repulse each other. So this repulsion is described by this part of the Hamiltonian. In red, U is the strength of the repulsion, and N is the quantum mechanical occupation operators. So basically telling the occupancy of this site. And the first term in blue is just the hopping, because electrons can hop or jump from one side to another. It's like kinetic term, how they hop from one part to another part. So the first term describes jumping from side to side, and the second term describes what happens when they are unhappy on the same side. So this is the Hubbard model for this fictitious system, and it was developed to describe strongly correlated materials, or what is known now Mott-Hubbard insulators. So basically, it's a class of materials that have d and f electrons, where plain DFT doesn't work, and you need this kind of specialized Hamiltonians. So this is actually iron oxide is one of the examples where this specialized treatment is needed. So okay, it's interesting that more or less in the same time in the history, two theories were developed independently from each other, and they didn't talk to each other. And 25 years later, in 1991, a group of scientists decided to try to combine these two theoretical methods. So they tried to merge DFT with the Hubbard model, and this is what is known as DFT plus U. Because basically they took the idea of the Hubbard model and incorporated it inside DFT, and they call it DFT plus U. So that's how historically things evolved. And this allows you to work to describe systems that are known as Mott-Hubbard insulators or charge transfer insulators. This is the case where, let's say, iron oxide and cobalt oxide and other materials, they can be called Mott-Hubbard or charge transfer insulators, where you have localized electrons. So what is the difference between Mott-Hubbard and charge transfer? Mott is another very famous physicist, and Hubbard too, but they both worked on the same problem. That's why it's called Mott-Hubbard. And the picture is the following. Here we have on the left an energetical picture. In Mott-Hubbard insulator, if you have on the left, you have D band, which is metallic. You see if it's with the gray, it means it's occupied. If it's white, it means it's empty. So D band is partially occupied, so it's metallic. And below there is a P band of oxygen, which is fully occupied. If you apply the plus U correction, like in the Hubbard model, apply it to the D band, you can split it onto the occupied component and empty component. And there is a band gap between these D subbands. And so whenever there is top of the valence band is of the D character and bottom of the conduction band is of the D character, so both are of the D character, so this excitation from valence to conduction would be from D to D, and this is called Mott-Hubbard insulator. But then there could be a case like on the right. Again, we have D band half populated and P band populated. When you apply plus U correction, what happens? You still split the D band onto occupied and empty, but this occupied one went down so much, it's even lower than the P band. You see the P band is this one. Now the D occupied one went lower than P band. And now what we have is the top of the valence is of the P character and bottom of the conduction of the D character. So now this transition would be P to D. And this is called charge transfer because there is a charge transfer from P states to D states. So from one type of states to another type of states. While on the left, it was from D to D. It's the same type of states. So it's called Mott-Hubbard. This is just a terminology to distinguish between Mott-Hubbard and charge transfer. And there are some cases where there is no clear distinction between the two. It's kind of hybrid between the two. It's not Mott-Hubbard or charge transfer. It's kind of a mixture of the two. It also quite often happens in the materials. So, okay, it's a bit different concepts, just to summarize. So this was a brief history of DFT plus U, how it was invented. And this is to show you where it is used for and how does it work. Basically, when you apply plus U, you can open the band gap in metals.
Excuse
Right?
me, Iurii.
Yes,
Please.
yes,
I'd like to ask about the charge transfer insulator.
yes.
This is a model to describe a system that happens. Happens in the reality, or this is a model that can is like hypothetical model of
So this happened.
simulation.
Thank you for the question. This happens in real materials.
Okay.
Like examples are iron oxide and cobalt oxide. So in iron oxide, I don't remember if it's Mott-Hubbard or charge transfer. I don't remember what it is. Probably it could be even the mixture of the two.
Okay.
So in iron oxide, if you use DFT with LDA or GGA, you will obtain a metallic solution. Actually, we have a hands-on today, but hands-on will be done for cobalt oxide because it's a bit simpler. Cobalt oxide is also metallic if you use LDA or GGA. And when you apply a plus U correction, you can split the D band and open a band gap. So it really happens in real materials.
Okay. And for this charge transfer, it can happen also on the cobalt and the iron.
Yes.
Thank you.
Yes. You're welcome. Any other question? There is a question in the chat. The question is, can hybrid functionals treat localized electrons in transition metal oxides accurately enough that do not need to use DFT plus U? The answer is yes. People can use hybrid functionals to describe the same problem. Yes. So DFT plus U and hybrid functionals, they do similar job. They're kind of, they do the similar job, yes. So both methods can be used to solve this problem. Sometimes they agree, sometimes they disagree. It's a very interesting problem to compare these two methods, but yes, hybrid function can be used to describe this problem, yes. And another question is, what is the main difference between Mott-Hubbard and charge transfer insulators? So the difference is what is the top of the valence band and bottom of the conduction band. If it's both are of the D character, you see is indicated here. So the Fermi level is between occupied and empty states. If both are of the D character, then you call it Mott-Hubbard. But if they are of different character, so here it's P states and D states, then you call it charge transfer insulator. Just that. It's just a convention, how people decided to call it. And then there is another question. So electrons don't jump. How does that affect the properties of the metal? Yes, you can see that way. The electrons don't jump. They stay localized. Exactly. So if we go back, so if you don't apply Hubbard-U correction, they jump. They can fly around. It's like a sea of electrons. They're free to move everywhere. But whenever you apply the plus U correction, you don't allow that, and you get this picture. They're localized. So they don't jump correctly.
There is also Nihad. She's raising her hand.
Yes, please.
Nihad, you can ask.
Hi.
Hello.
Can the same material jump from or change or transfer from Mott-Hubbard to charge transfer insulator?
Thank you. It's an interesting question. I never thought about this. I think it should be possible if you apply some pressure to the material, or so basically to achieve that, we need to move states, right? So for example, if you have Mott-Hubbard and it's DD, but what you want to do is to move this D band below P band. If you can do that, then yes, you can do that. So how to do that? I don't know actually how to do. Maybe I would say pressure. Maybe if you apply pressure, you can change it, but I'm not sure actually it's so easy to do because it's quite drastic change. I mean, to change the order of states, it's pretty complicated. To be honest, I'm not sure how to do that, but I would say maybe it's possible, but maybe with pressure, maybe something else. But I never thought about this question. It's quite interesting. In any case, it's just a terminology. Often they coexist. These two, as I said, could be a hybrid case when it's not clearly Mott-Hubbard or not clearly charge transfer. It's kind of something in between. So we cannot really say it's one or the other. It's kind of both. So that's the very typical situation. And then maybe when you apply some pressure, you can kind of lean it to one side or to the other side, and then it's okay. Now we are not hybrid. Now we are mostly mod Hubbard, or we are mostly charge transfer. Yes.
There is also another question by Rania.
Yes.
Rania, you can ask.
How can we know we will apply the Hubbard model using the DFT plus U? Is it when we have the D or F electrons we should apply it, or what's the characteristics that lead us to use this?
Okay. Yes. So when do we need to
When
use
should
it?
I have to apply it?
Yes. Good question. So you should apply it when you have. So this is the answer to when do we need DFT plus? When you have transition metal compounds, let's say iron, cobalt, nickel, manganese, chromium, vanadium, titanium, with or other elements below, combined with, let's say, oxygen, or typically with oxygen, it's called oxides, but also you can combine with sulfur, sulfides, and other materials. So whenever you have combination of transition metal and these elements, let's say oxygen, sulfur, and so on, then you can have that case with DFT plus U is needed. If you just have pure cobalt is metallic, we don't need it. If it's pure iron, it's metallic, we don't need it. Pure nickel, it's metallic, we don't need it. I mean, these are transition metal elements, they're metals. So we don't need any Hubbard U. But if you combine it with oxygen or sulfur, the properties of the material change. All of a sudden, they are not metallic, but they are insulating, like mod Hubbard insulator or charge transference. And there you do need plus U to describe that localization. It's very interesting, actually, how it changes. Okay. Any other question?
I think there is no. Maybe we can continue.
Okay. I think we'll have new questions as we move forward. But I'm happy that there are many questions. Please don't hesitate to interrupt me. So now, a little bit of theory. I don't know if you like theory and equations or not, but I'll show you a little bit of equations to understand a little bit better how it works. So now that we know the history of DFT plus U and why do we need it, now how it actually works. What's the main idea mathematically speaking? So the idea is very simple. As I said, we want to combine the Hubbard model with DFT theory. So how to do that? It's very simple. So you take the DFT energy, which is blue, and it depends on the density. Here I show density as rho. Before I call it N, but now I call it rho. Sorry for this inconsistency. But rho is the charge density and depends on spin sigma. Can be sigma spin up or sigma spin down, and position of R. So this is the DFT that we know. You learned about it in the school previously. Now, how do we combine it with the Hubbard model? So we add the Hubbard energy, like in the Hubbard model. Like this red term here, you see the Hubbard U term. So we kind of want to take this red term and put it inside of DFT, because that term is describing electron repulsion when there are two electrons sitting on the same side. So we put it inside of DFT. But little problem appears here. In DFT, we already have full description of the system. There is total energy of the system. And we are adding a little bit of more energy. We cannot do that. There is conservation of energy in nature. We cannot simply take and put a random number of energy into the system. It's like, you cannot do that. There is conservation of energy. So, but if we do that, we need to subtract something. So we subtract the so-called double counting. So let me explain a little bit. So in DFT, we already described these 3D electronic interactions. But we're adding a better description of 3D electronic interaction, the red term. Then we need to subtract from the blue term the wrong description of 3D electrons. 3D electron wants to delocalize because of self-interaction. But now with the red term, we describe the correct localization of 3D electrons, like in Hubbard model. Okay, fine. But now we need to remove from the blue term the wrong description of 3D electrons, and that's called double counting. So now we are fine because we add the correct description and remove the wrong description. That's it. All the rest of DFT remains the same. So how to make an analogy? Again, let me make an analogy with maybe some medicine. Let's say in a human body, there is kind of some little problem and we want to remove it. So we remove it. Maybe a tooth. In the tooth, you have a caries. You remove it, but then the doctor fills it in with this white thing, right? To make the tooth look like it should. So we remove the bad part and put in the good part. But the rest remains the same. So that's how it works. It's very simple. And actually all genius things are very simple. That's it. Now we can massage a little bit the red term and the black term. So we can actually mathematically manipulate a little and rewrite it as a one term. And that term would be E of U. And it's shown here. So this Hubbard correction energy mathematically looks like this. It's 1/2, nothing special. Then we have summation over I, M prime sigma. So what is I? Capital I labels atoms. Basically, it enumerates atoms. Sigma is spin, can be up or down. And M and M prime are the so-called magnetic quantum numbers. They label Hubbard states. So let's say in 3D states, we have d electrons. So the orbital quantum number is 2. And magnetic quantum numbers can be +2, +1, 0, -1, -2. So there are 5 magnetic quantum numbers. So M and M prime are magnetic quantum numbers that can be from -2 to +2. And there are 5 of them. Now we have this Ui and Ji. So Ui is the Hubbard parameter and J is the Hund's parameter. We'll talk a little bit later about it. So U describes electrostatic repulsion of electrons and J describes Hund's interaction of opposite spin electrons. Anyway, we have U minus J, which we can call U effective. So we can call it as effective Hubbard parameter. It's just a constant that we don't know. Then we have Kronecker symbol, delta M prime. So just to remind you that this delta M prime equals to 1 when M is equal to M prime, and it is equal to 0 when M is different from M prime. Then we have minus N I sigma M prime multiplied by the same object. So this N of I sigma M prime is a matrix. It's called occupation matrix. It's shown below. And it's a very important object in DFT plus U. It's really, really important object in DFT plus U. It's a very useful object. So it's occupation matrix, which tells you the occupancy of the 3D shell of the iron atom in our example. So it is defined as sum over band indices V and K points that you know already. Then F, sigma, Vk are the occupations of quantum levels, such as Fermi-Dirac, Mas-Fessel-Paxton, or Marzari-Vanderbilt. I think if you had lectures on metals in DFT, you should have heard about these names like Fermi-Dirac, Mas-Fessel-Paxton, Marzari-Vanderbilt. Just basically it can be 0 or 1. If it's 0, it's empty. If it's 1, it's occupied. So basically how much these quantum states are populated. And then we have 2 scalar products in Dirac notations. We have psi, sigma, Vk, which are the quantum wave functions, depending on spin, band index, and K point. And phi are the localized orbitals. It could be atomic or Wannier functions. So what does it mean? We are projecting quantum wave functions psi onto localized orbitals. could be, let's say, atomic orbitals. So if we stay with our example, iron oxide, phi would be the atomic orbitals of iron, 3D atomic orbitals of iron. So we're projecting Conchem states or block states onto the 3D atomic orbitals of iron. And this should tell us the occupation of the 3D atomic 3D shell of iron. If you take a trace of this matrix, so you sum up our so you take summation of m and sigma, so you sum up our spin up and spin down, and you sum up the diagonal elements of this matrix, you will obtain a constant which tells you how many electrons are sitting on the D shell, 3D shell of iron. So it's a little bit complicated, but in hands-on, you should see this. In the quantum ESPRESSO calculation, in the output file, all these occupation matrices are printed. So the full matrix is printed. Let's say for the 3D electrons of iron, it will be a matrix of size 5 by 5. And if you take a trace of this matrix 5 by 5, basically sum up the diagonal elements, it will give you a number that is the total occupancy of the 3D shell of iron. So, okay, we know now occupation matrix. It's a very fundamental property in DFT plus U. And then we have also the U parameter, effective U parameter that is not known. So this Hubbard U parameter, but also this projectors phi are free to choose. The theory doesn't tell you what are those. So you can choose the value of Hubbard U, and you can choose how to represent your localized basis set. It can be atomic or Wannier. So that's kind of flexible on the one hand, but on the other hand, it also creates a little bit of problems because we don't know what is the Hubbard U. We need to choose it somehow. And localized basis set, again, you can choose it. So everybody can choose different localized basis set. And then when we want to compare results, it's not easy to do because we have different choices. Any questions about this equation so far? Okay. If not, so now let's try to understand a little better how it works. So this blue text explains what does it do actually, this energy correction, Hubbard energy correction. So the total energy is minimized when n is idempotent. That is to say the eigenvalues are 0 or 1. So yeah, there is a question, but just let me finish this.
Okay, so
yeah. So okay, why is occupation important in magnetic materials? So occupation is important because I mean, in this Hubbard correction energy, we have this occupation present. So depending on the value of occupation, the energy will be different. It's good to maybe to explain on the specific example, but it will be done in a hands-on. That's exactly why we have the hands-on, to have a feeling of how it works. But occupation is needed in the formulation of DFT plus U because basically in iron oxide, we want to correct 3D electrons because they are over delocalized. So all the rest of the electrons we don't want to touch. So how to do that? So we take the full block wave function in your solid and you project it onto 3D states of iron, and then you shift them by Hubbard U. That's how it works. And occupation matrix does that exactly. You take Conchem wave function or block wave function, you project onto 3D states of iron, and then you scale it by the Hubbard U, and then basically you shift them. So you can split them. All the other states are unaffected. So this kind of targeted action on specific states that you want to fix. That's why we need occupation matrix. I hope that was clear. So coming back to get a bit of a feeling of how this energy works. So this energy can be actually 0 and it also have a maximum. So it's 0 when n is 0 or 1. So when you have n 0, because when is 0, you multiply by 0, you get 0, right? Or when n is 1, it's also the energy is 0 because you have 1 minus 1 is 0. So this Hubbard corrective energy has 0 value whenever your occupancy is 0 or 1. So basically you don't do anything. But whenever n is partial, so between 0 or 1, so let's say 0.5, in that case, exactly at 0.5, the energy would have the maximum value. So that's when you activate this Hubbard corrective energy. Basically, it's the maximum penalty. So this energy, Hubbard corrective energy, acts like a penalty. Whenever your states are already fully occupied or empty, 0, 1, you don't touch them. But if they are fractionally occupied, like 0.1, 0.2, 0.3, and so on until 0.9, all these states between 0 and 1, you actually act on those states with the correction. Okay, if it's okay, any questions so far about this Hubbard corrective energy? Okay. Now, how do we solve Conchem equation? We need to modify it actually because of the Hubbard-U correction term. So this is what we know. We have kinetic energy, Conchem potential. Conchem potential depends on local, non-local part of the external potential, Hartree and exchange correlation. For Hartree, we know the expression. For exchange correlation, we use approximation, let's say LDA or GGA. And these potentials depend on the density, rho. Fine. So we are familiar with Conchem equation and that we need to solve it self-consistently. This is what you already know from previous days. Now, in DFT plus U, what changes? We have extra potential, the red term. It's called Hubbard potential. So we need to insert it into Conchem equation. This Hubbard potential has this expression, U times Kronecker symbol divided by 2 minus n multiplied by the projector. And here it depends on the occupation n, occupation matrix that we already saw previously. And so we still need to solve this modified Conchem equation self-consistently. Because why do we solve it self-consistently, iteratively? Because to solve equation, we need to know the potentials. To know the potentials, we need to know the density and occupation matrix. To know the density and occupation matrix, we need to know the wave function. But we don't know a wave function. The wave function is exactly what we want to find from Conchem equation. So it's a closed loop. So we want to solve it, the Conchem equation, but at the end of the day, we need to know the wave function. But wait a second, this is exactly what I want to obtain from by solving the equation. It's a closed loop. That's why we do it iteratively, self-consistently. We compute at first iteration, then we update, we compute, we update, and we do it until convergence. Exactly in standard DFT, but now we have this Hubbard potential also updated at every iteration until self-consistency. Okay, a little recap. So in DFT plus U, we have this corrective energy, Hubbard corrective energy. The Hubbard U parameter is unknown. Then we have occupation matrix, we defined it. And this was introduced in the 90s. The first work in 1991, then there was another modified formulation 1995, and then another simplified formulation 1998. So there are like several works. It was quite a boom for DFT plus U. It was born in 1991. There was a lot of boom, a lot of activity. Many people tried to improve and very excited, very beautiful. And then in 2010, there was proposed formulation or extension of DFT plus U, which is called DFT plus U plus V. Now we have not only the Hubbard U correction that wants to localize electrons. So there is this cartoon at the bottom. In DFT plus, in simple DFT, you have like a Gaussian delocalized electron. And when you apply plus U correction, you localize it. So it becomes like squeezed Gaussian, more localized. So it's the Hubbard U corrective term that we described. But then we can add another term. It's called the plus V correction, or actually minus V, correction. This describes interaction between two atoms. So the U term describes electron on one atom. So what happens inside, on site term? V describes interaction between two atoms, let's say between iron and oxygen. So it's called intersite interaction. Let's say 3D states of iron interact with 2p states of oxygen. So the first term, the U term, wants to localize electrons. It wants to squeeze them on the atom, while the V term wants to push them back a little and restore the hybridization with p states of oxygen. And these two terms are competing. The U term wants to localize electrons. The V term wants to delocalize them, wants to kind of keep the covalent hybridization with ligands. So oxygens are called ligands. And this extended formulation, it gives you even more flexibility. It's like, imagine an airplane with a lot of buttons. You know, the more buttons you have, the more control you have. If you have just one button, how about you? Okay, you can maybe with one button, you can fly on your airplane, but you can crash maybe. But if you have U and V, you have more buttons. You can have more things to fine tune your airplane. And it has actually, in reality, works more accurately. DFT plus U plus V works more accurately than DFT plus U when you have covalent interactions, when this hybridization is important. And it's very nice. This theory is very nice, but there is again a problem. So we don't know what is the U parameter. We don't know what is the Hubbard V parameter. And we need to decide what is the projector's phi. So it's like in DFT. Okay, so yes, there is exact exchange correlation functional, but we don't know it. Okay, so what do? We try to approximate, we try to do something about it. In DFT plus U and plus V, the same. Say, okay, there is this corrective energy, great. But again, we need to decide somehow how to choose Hubbard U and V, how to choose the projectors or localized basis set. It's always like that. You try to do something, but again, you need to choose some parameters or some parameterization of your functional. Yes, and it creates a lot of headache and problems, but okay, that's part of life. Any questions so far? Because we go deeper and deeper into DFT plus U and plus V. Was it clear enough, this introduction to DFT plus U? The Hubbard energy, so Hubbard corrective energy, occupations, parameters. Okay, so before the next break in about 5 to 10 minutes, let's introduce other points. So let's try to discuss the first problem. Hubbard U and V are unknown. So how do we determine them? There are several ways how to go about it. The first one, fit into experiments such as magnetic moments or band gaps or oxidation enthalpies. So basically you try to tune your Hubbard U parameter and V if you want, trying to match some experimental properties such as band gap or magnetic moments, for example. That is empirical approach. It's very popular. Many people use it because it's simple, especially for band gaps, but it requires a separate discussion whether that makes sense or not, because DFT plus U was not designed for the accurate band gap predictions, but still people do that. Another strategy is to try to tune it, Hubbard U, not to experimental properties, but rather to properties computed using other advanced methods, such as hybrid functionals, HSE06 or PB0, or other advanced methods like GW. It's many-body perturbation theory. So you can try to match Hubbard U and V to something that you know from experiments or other calculations. But the most beautiful, I would say, is just computing ab initio or from first principles these parameters. And there are different methods on the market, such as linear response theory, constrained RPA, and Hartree-Fock-based method, ACBN0. So nowadays you can compute Hubbard parameters ab initio using these methods. And moreover, now we're talking about material science in the era of AI. People use machine learning across all of this to machine learn Hubbard parameters. But that's an entire different conversation. So I will present to you how to compute Hubbard parameters ab initio using linear response theory. But there are also other methods, but I will not cover it in the lecture. Before we go to the discussion about linear response theory, let me also present this most important slide of the whole lecture. So I really hope that you take home the following information, that Hubbard parameters are not universal. Why? Because computed parameters, they depend on many aspects, such as type of Hubbard projector functions. So basically the choice of the localized basis set when you compute occupation matrix, if you use atomic orbitals or Wannier functions and so on, you will get different values of Hubbard parameters. So they are not universal. It also depends on the choice of pseudopotential and oxidation state. So if you change pseudopotentials from one library to another library, your, again, actually Hubbard projectors change. And so as a consequence, Hubbard parameters will be different. It also depends on top of which functional you apply the Hubbard U correction. Is it LDA or GGA? So if you use LDA plus U, you might have one value of Hubbard U, but if you switch to GGA plus U, you will have a different value of U. So it's also sensitive to the base exchange correlation functional. And finally, whether you compute Hubbard U parameter self-consistently or in one-shot fashion. So this I'll tell you in a moment what it is. So the take-home message is that the Hubbard parameter is not universal. For example, if you take iron and use it in iron oxide, so Hubbard U in iron oxide would be a certain parameter, let's say 5 electron volts. But then if you take another compound, let's say the one we mentioned before, lithium 0.5, iron, phosphorus 0.4, it's still iron. But the Hubbard U will be different. Even more so, it will be different for different oxidation states of iron, because we have here iron 2 plus and 3 plus, and they will have different Hubbard U. So Hubbard U is really material dependent and oxidation state dependent and so on. So it's not universal. There is no one magical number that you can use across all iron compounds as an example, but it also applies to other materials. So Hubbard U is not universal. It must be computed every time for every system. Okay, now we are coming to the discussion how to compute Hubbard U ab initio. But probably at this stage we can make a little break. Before we go on a break, any other questions up to now about DFT plus U? Okay, if not, I propose we take a second break.
Okay.
And we reconvene at 11, so in about 8 minutes, if it's okay.
Okay, yes.
Okay, if you have any questions, we can start with questions after the break.
Yes, for the participants, you can write your question in the meanwhile, and when we start, we can answer the questions. Yes, thank you.
Perfect, thank you.
There is a question in the chat by Aposantal. What is the main difference between DFT plus U and DFT plus U plus V?
Okay, thank you for the question. So DFT plus U plus V is the same as DFT plus U, and the only difference is that you have extra correction, this second one. So you see, if you compare DFT plus U plus V with DFT plus U, you have DFT plus U term is identical. We just have extra term that describes physics that is not described in the DFT plus U, namely the intersite interaction. So that's the only difference. In DFT plus U, so everybody knows DFT plus U, but DFT plus U plus V is less known. But in the recent 5 years, it became more and more popular. Now many people realize that it's nice. It gives you more accurate predictions. So more and more people use DFT plus U plus V. And in Quantum Espresso, it's implemented. So you can really use it for your research if you're interested. Yes. Okay.
There is also Nihat. And Nihat, you can ask your question.
I just cannot get the idea of that U is not universal. For sometimes, can two researchers use different type of BCD components or different types of projection and get different values? How can we compare with them with each of the results?
So yes, if you have two researchers, one using Quantum Espresso, let's say you use Quantum Espresso, you use atomic orbitals, and you get Hubbard U of 5 electron volts. And your colleague uses another code, let's say WASP, with different type of projectors, not atomic, but there is kind of more complicated type of projectors. And your colleague obtains, instead of 5, let's say 6 electron volts. And then you start, but you both study exactly the same material, let's say iron oxide, but you get 5 and your colleague gets 6. So who is right, who is wrong? The answer is nobody.
Yes, exactly. Who is right and who is wrong?
Yeah, nobody is wrong, because it's okay, because you use two different codes and you use two different projectors. So where is the projector? Let me find here. Since you use different projectors and you compute Hubbard U ab initio, you get different Hubbard U, because when you compute it, it depends on the projectors. That's exactly what we'll see in a moment. But nobody is wrong. I mean, you're both right. It's just you use different projectors, which are used in different codes. Yes, but that's you. When you publish your paper, you have 5 EV, and your colleague publishes a paper at 6 EV, and then it might be a bit misleading. Oh, what's going on? Who is right? Who is wrong? Nobody is wrong, because you use different codes and different projectors. But some people forget about this, and they just, let's say, it's very often happening that, let's say, somebody published a paper with DFT plus U and using, let's say, WASP, and they report value of U, let's say 6 electron volts. But then someone, like, let's say, takes another code, Quantum Espresso, and say, oh, in that paper they use 6 electron volts, so I will use the same value. But that's wrong, because they use different code and different projectors. So the Hubbard U is not transferable from one code to another code because of these different projectors. Many people forget about it, or they don't even know about it. So that's very, very important. That's why here I really try to stress that Hubbard U is not universal. It's not transferable from code to code. It's really, when you choose the code, you choose specific pseudopotentials. Even if both colleagues use the same code, Quantum Espresso, but they use different pseudopotentials, that's also will give different Hubbard U. So when you choose the code, Quantum Espresso, you choose the pseudopotential library. And then again, even if you do that, Both colleagues use the same code, the same projectors, the same pseudopotential, but you use LDA plus U, but your colleague uses GGA plus U. So you'll have different U again. So it's very depends on many technicalities. Yeah, so you need to be careful. Many people confuse and forget about it. Yes?
Good. There is a question also in the chat, two actually. When Abu Sandal, he's asking, what does DFT plus U plus V improve in oxide perovskites?
Yes. So DFT plus U plus V improves the hybridization. So where is it? Here. It improves the intersite interactions. So the plus V term is needed when you have covalent bonding. So if you know the difference between ionic bonding and covalent bonding, so in ionic you have like electrons localized on transition metal and they don't hybridize a lot with ligands, with oxygens. So in that case, plus U should be sufficient. But if you have covalent bonding, which means there is a lot of interactions between, let's say, central atom and ligands, so they kind of hybridize and overlap. So in this case, you need plus V. So from our experience, you need plus V when you deal with covalently bonded materials. And all properties improve, like voltages in batteries improve, phonons can improve. You will learn about phonons in the next days, I think, and so on. So yes. And then there is another question.
By noon, Adam, she's asking, why does the Hubbard correction term become maximum for partial occupied orbitals and zero for fully occupied or empty states?
Perfect. Good question. This is shown here. So how to do it? So basically you can see it from the expression of the energy. I don't know. I wanted to use some drawing, but it's a bit complicated. Or maybe I can do it. Let me try. Sorry. Let me draw. So let's say you have a function of x. Do you see my writing, right? And the function is 1 minus x multiplied by x. So this is a simple function, right? So when you plot this function, f is a function of x, and say when it's 0 and 1, it will look something like this. So when x is 0, function is 0. When f is 1, function is 0. And when x is 0.5, it will have the maximum. So it behaves like inverted parabola. So physically, meaning, why do we like this physically? Because when x is 0 or 1, it means, so when x is 0, it means it's empty electronic states. When x is equal to 1, it means it's occupied electronic state. So Hubbard-U correction does not act on states that are fully empty or fully occupied. It doesn't touch them because it's already happy with that. If instead you have something between, so when x is between 0 and 1, in that case, Hubbard energy starts acting because it starts to penalizing the metallic solution. Because when x is between 0 and 1, it means it's a metallic solution, it's fractional. In that case, Hubbard-U doesn't like metallic solution. It wants to destroy it or kill it. So it really penalizes when x is between 0 and 1. So it's really designed that way. When it penalizes fractional occupations, it tries to kill the metallic solution. So if you go back to this mod Hubbard, sorry, let me remove the drawing. So remember this mod Hubbard and charge transfer. We have metallic solution. on the left, which means x is between 0 and 1. It's fractional. And we don't like that. So we want to apply place correction to penalize metallic solution. And when you do that, x becomes 0, empty states, or x becomes 1, occupied state. So when you apply plus u, you go from partial x to x is 0 or 1. You really act it like that, mathematically speaking. I hope that was answering your question. And then there was another question. Is there any relation between u and some experimental parameters? If yes, how could someone get a value close to the experimental one? So at the end, so at the beginning, people tried to make a link between Hubbard U and some experimentally measurable quantities, basically from atomic physics. But I think that is not really the right way to go. I think there is no direct link between Hubbard U and anything experimentally measurable, because Hubbard U, it's not a measurable quantity. It's really the quantity that tries to cure the drawbacks of exchange correlation functionals that are approximate. So Hubbard U is really the quantity that tries to remove self-interaction errors. I'll show it in the next slides, basically how we compute it. And self-interaction errors are unphysical. They don't exist in nature. So Hubbard U is something that is to fix pathological or anomalous, that exists purely theoretically. It's really, we know there is this approximate exchange correlation functionals that have unphysical self-interaction errors. So none of this exists in nature. It's just the drawback of theory, approximate theory. And U is really to fix this pathology of theory. So it's not something that can be measured experimentally. Yes, yeah, exactly. I hope that answered your question. Okay.
Thank you. There is also Nihad. She's raising the hand.
Please.
Again, I know that U is affected by oxidation state. One of the factors that affected you. How it's affected by oxidation state? Is it increases as oxidation state increase, or what? What is the relation?
Thank you for your question. So it's a very nice question, but I don't have it, my slide here. I need to find another lecture. Just give me a second. I need to find it. I just take one of my other lectures where I have some examples of applications. So let's say if we take batteries, because in batteries we have a lot of change in oxidation state. And let me just jump. I have some demonstrations how oxidation state change, and we don't have time for that, but oh, I don't have here. Okay, maybe I can take this example, why not? So this is a compound. Which compound is this? It's nacicon, sodium, vanadium, phosphorus, oxygen. It's my PhD student Stefan Sharon is working on it in collaboration with Manuel Dillens from Denmark, DTU. So in this compound we have vanadium. It's a transition metal element. And vanadium also changes the oxidation state as we remove or add sodium. And this is written in this slide. You see when we go from left, 25% of sodiation, to the right, 100% sodiation. When we increase sodiation, vanadium goes from left, which is vanadium 4+. Sorry, I don't have the pointer, so I need to go in this mode. Just a second. So we go from left where vanadium is 4+ and Hubbard U is 6.4 electron volt. Then we go to the right where, let's say go to the 50% sodiation. We have there are still half vanadium are 4+, but 2 of vanadium changed oxidation state from 4+ to 3+, because they received one extra electron from sodium. And you see how Bardew changed from 6.4 to 5.5. And then you keep increasing sodiation. So now all vanadium are 3+, so which is 5.5 eV, how Bardew. And then if you increase sodiation to 100%, half of vanadium change oxidation state to 2+, which is Hubbard-U 5.1. So these are the ab initio Hubbard-U. So in yellow at the bottom.
Always decreasing as the oxidation decrease.
Yeah. Yeah, it decreases, yes. One can try to understand why it happens. One can try to understand why it happens. So when you decrease oxidation state, you are adding more electrons to your vanadium, right? So you have more and more electrons in vanadium. And those electrons, they increase the screening, electronic screening. So electronic screening of Coulomb interaction. So as a consequence, this Hubbard-U goes down. I think that could be one interpretation. Yeah. So when oxidation state decreases, Hubbard-U decreases. It's a good question. Okay, let's go back to our lecture. Other questions?
I think there is no question. We might continue.
Okay, good, good. All right, so let's move forward. So now how can we compute the Hubbard-U using linear response theory? This linear response theory is based on the idea of linearity of the energy. So this is just schematics. Imagine, let's say, iron oxide, okay? Our example that we use throughout the lecture, iron oxide. Suppose this circle, it's iron, okay? It's actually not really iron because we have 5 levels. So these black horizontal lines are levels of 3D shell. And on every level, we can have 2 electrons. So blue circles are electrons. 2 electrons because of Pauli exclusion principle. We can have on one level 2 electrons with opposite spin, up and down. And this is more like a copper, because in copper we have 10 electrons in the D shell. So let's say it's copper oxide, to be more precise in this example. And suppose we take 1 electron out. So we take it from this level of 3D level of copper outside the atom. So all the blue area, we call it electron bath. It's like the rest of the solid. Let's say you have copper oxide, a lot of copper atoms, a lot of oxygen atoms, so it's a crystal. And then we are looking at only 1 copper atom inside the crystal. And what we are telling here is that we take 1 electron from copper atom and put it outside to the rest of the crystal, which we call electron bath. And what we are saying here is that the energy must change linearly when we're removing electron from copper to the rest of the solid. So that's there is no theorem about it. It's like heuristic statement, but it makes a lot of sense. Like energy in nature changes in a linear fashion. Why would it change quadratically, cubically, polynomially, exponentially? I mean, for electrons, it should be linear. Makes sense kind of intuitively, but there is no any strict theorem that tells this or prove this. So based on this idea, now we can compute Hubbard-U ab initio based on so-called linear response theory. So how does it work? It's very simple, elegant, and that's why it's so popular. On the left, top left, I show you the energy expression in dft plus u. I dropped the summation over atoms. There is, let's say, only 1 atom for simplicity. And I already said that there is a heuristic statement that energy changes in a linear fashion when we move an electron from the Hubbard manifold to the rest of the system. And on the left picture at the bottom, I'm showing you we already seen it before. The exact solution must be piecewise linear. That's exactly what dft plus u is giving. while approximate DFT gives a quadratic-like behavior. So the plus U correction is basically removing this curvature and putting in the linear behavior. So the U correction is this dashed parabolic-like correction. And interestingly, at integer number of electrons, n and n minus 1, the Hubbard U correction is 0, because as we discussed previously, when x is 0 or 1, there is no Hubbard correction. So Hubbard corrective energy is 0. So we have correction only between integer numbers. So what we are doing here, we are removing the curvature, this parabolic-like curvature. And mathematically speaking, the curvature is described as the second derivative. So you have energy, you can compute first derivative, and then you can compute second derivative. So the curvature is described by the second derivative. And we request that the second derivative is 0. This would mean it's a straight line. There is no curvature. So that's very simple. We have energy expression. All what we request is that there is no curvature because it's unphysical. And based on this condition, so d2e over dn2 is 0, and the analytical expression of energy on the left, we can compute second derivative and equalize it to 0. It's a simple homework, you can do it. So you take this expression on the left, you compute first derivative with respect to n, and then compute second derivative with respect to n. And you will find that the u is equal to so second derivative of the DFT part energy with respect to the occupation. So that's how Hubbard U can be computed ab initio, as a second derivative of the DFT part of the energy. That's it. That was proposed by Matteo Coccioni, Professor Matteo Coccioni, who is now working University of Pavia in Italy, and Professor Stefano De Gironcoli, who is working at SISSA in Italy as well, in Trieste. Yeah, that's very simple, and it's very popular method. It's implemented in VASP, Quantum ESPRESSO, and many other electronic structure codes. It basically tells you how to compute Hubbard U ab initio. And I also forgot to comment about this figure on the right. That's the first derivative of the energy. And this is to show you this discontinuity when you add Hubbard correction. So if you use DFT, you have parabolic behavior, and the derivative of parabola would be just a straight line. But if you have DFT plus U, which is piecewise linear, the derivative would be like this behavior on the right. You see there is discontinuity, there is a jump at the integer number of occupations because there is a change in the slope of these straight lines. So if it's a straight line, it's just derivative is constant, but then there is discontinuity in the derivative, and there's the jump, another constant jump, another constant. So what it effectively does, the Hubbard U correction introduces discontinuity into the functional. And that's why also the band gaps are improved in DFT plus U. Now, how does it work in practice? And originally, one had to use supercells because in practice, you need to apply perturbation to your atom, highlighted in yellow. And perturbation, it would be like introducing a defect in your system, kind of one atom is special. So that's why we need to use supercells in periodic boundary conditions to avoid unphysical interactions between perturbed atom and its periodic images, because it will be repeated in 3 dimensions. And practically, one has just to add a perturbation term in your Conchem equation, where lambda is the strength of the perturbation, and V is the perturbing potential. It's simply a projection onto the localized basis set, exactly the same localized basis set that we use in occupation matrix. Let me go back. So you see this localized basis set phi, let's say atomic orbitals, it's exactly, we use this as a perturbation, just a projection on the 3D states, and lambda is just infinitesimal constant. So physically speaking, we just shift by lambda the 3D states of iron and see how the system responds to this perturbation. And Based on this, we can determine Hubbard U by measuring the change in occupations, delta n, divided by delta lambda. This gives you the response matrix, chi. And then we invert it, so chi minus 1, and subtract non-interacting analog, and we obtain Hubbard U, which would be the diagonal matrix elements. And V would be off-diagonal matrix elements. So this approach is computationally expensive because you need to use supercells. And sometimes you can have convergence issues when dealing with large supercells for very complicated magnetic materials, might be troublesome. And it could be a bit cumbersome to use in practice because you need some post-processing codes for that. And this can be reformulated in a better way. So this is a little bit complicated slide, but we're towards the end of the lecture. So on the left is what we shown just before. So on the left is the same as here. So we can go from the left to the right, and on the right, I'm showing you other way how to solve the same problem, but more efficiently. So on the left, we have a perturbation, and then we measure the linear response of the system. So we can do it more efficiently using the so-called density functional perturbation theory. And instead of solving the equation on the left for two values of lambda and using finite differences, we instead can solve first order perturbation theory equation. So it's called Steinheimer equation on the right. So basically you expand in Taylor series your perturbed equation on the left and keep it to first order. And this gives you equation on the right. It's called Steinheimer equation. And then instead of using supercells, you can use primitive unit cells, but with multiple monochromatic perturbations modulated by the Q vector. So I apologize, it's a little bit complicated and involved. I don't want to go too much into details. But at the end of the day, it can be shown, if you're interested, we can discuss more, or there are papers on that, showing that this approach, which is computationally expensive, can be reformulated efficiently using density functional perturbation theory. And this is exactly what is implemented in the HP code of Quantum Espresso that you will use for the tutorial today. So the main idea is that you use primitive cells, and in combination with monochromatic perturbations, it's computationally much less expensive, easier to converge, and user-friendly and automatic. And to show you why is it better, first on the left is the scaling, basically computational cost. So the black line shows you the scaling if you use the old approach with supercells. You see it goes up very quickly as the size of the supercell. And the red one is the new one when you use linear response without supercells, with DFPT. You see the speed up could be 52 times for the supercell size 4x4x4, or the equivalently the grid, Q grid 4x4x4. So you need to use the Q point grids, and the size of the Q point grid corresponds to the size of the supercell. And if you use symmetry, you can speed up even more. And on the right, I'm showing the comparison of old approach, so linear response with supercells versus the DFPT, density functional perturbation theory, with primitive cells. And they give Hubbard U that are the same within the numerical noise. So for example, if you take a supercell of size 2x2x2 and use K-mesh 6x6x6, you get U value of 7.895. Equivalently, you can use a primitive cell. So you don't need supercell 2x2x2, you use a primitive cell, but you need to increase the K points 12x12x12 because there is a factor of 2 between primitive cell and supercell. And this would be equivalent calculations, but the DFPT calculation is much faster. But you see Hubbard U is the same within the numerical noise. And it's implemented in the HP code which is part of Quantum ESPRESSO and that we will use during the hands-on today. And one of the final notes on the Hubbard projectors. So let me make a link with what I've shown. So you see this yellow part, this localized basis set. I told you that the DFT plus U approach doesn't tell you that which one you have to use. It's free, it's up to you, or what is available in electronic structure codes. And this is exactly the slide about that. There is an entire zoo of Hubbard projectors. I just show you some examples. First one are so-called non-orthogonalized atomic orbitals. So they are provided with pseudopotentials. But the drawback, if you use non-orthogonalized one, when there is overlap of atomic orbitals between atoms that are not orthogonalized, you can have Hubbard U correction counted twice. So it's not the best type of projectors. Second type are orthogonalized atomic orbitals, where you use a loading orthogonalization method with these equations, where you basically orthogonalize atomic orbitals between all atoms. And that is much better, and we recommend to use orthogonalized atomic orbitals. It's called ortho-atomic, ortho/atomic in Quantum ESPRESSO. And the third example I would like to mention are maximally localized Wannier functions. There is a call called Wannier 90 that you can use to build different types of Wannier functions, look like this. And you can use also those functions as projectors in DFT plus U. And if you use these different types of projectors, you will have different Hubbard U. So you need to be careful. I mean, that's what I told at the beginning, that depending on the choice of Hubbard projectors, you will have different Hubbard U. And this is just to show you how they look like, let's say for iron oxide. So the first column in purple are the NAO, non-orthogonalized atomic orbitals. It's option 1. You see they're like kind of spherically symmetric, kind of in the plane. It's the top view, and the bottom is the side view. You see it looks like that. It's like the DZ square atomic orbital. Yeah. And then in the middle is the orthogonalized atomic orbitals. You see they change their shape. Now they are not like spherical, but they feel the presence of oxygens. So the green as a surface is kind of going perpendicular to the bond because we orthogonalize the oxygen. So these atomic orbitals, they are aware of neighbors. And the side view also shows you how it's modified. And final example are Wannier functions, in particular so-called frontier ones. You see how they look like completely different from the other two options. Now you also can have components on oxygens. So it's very interesting type of orbitals that one can use in DFT plus U. And they have their own advantages, which I will not discuss now. And we are working a lot with this last type of projectors in yellow because they are opening quite interesting physics, which cannot be described with purple or green orbitals. So you see, these are the different types of orbitals. And when you compute Hubbard U for each of them, you'll have different values of U. And okay, the last two slides. So this is the slide about cell consistency. So let me go back to make connection with previous. So you see at this important slide at the bottom, there is cell consistency. You can do it one-shot calculation or cell consistent. So let me explain now what it is. This is a slide about that. So on the left, I'm showing you the workflow to do the self-consistent calculation of Hubbard parameters. So the workflow is as follows. You start from the top, where you have initial crystal structure, let's say experimental one or from some databases. And for this crystal structure, you want to find the Hubbard U and Hubbard V. So how to do that? You need to follow several steps. First step, you need to perform structural optimization using DFT plus U plus V. Suppose you don't know U and V, so you set U equals 0 and V equals 0. But you can also start with some initial guess. But suppose we don't know U and V, we put it to 0. So we just perform structural optimization with DFT, which is, let's say, LDA or GGA. Fine. Now you optimize the structure, you compute the forces, stresses, you learned about that. Now you have fully optimized structure. Now we do the SCF ground state calculation again with DFT because we don't know U and V. So you do self-consistent field SCF ground state, and then with PW.X. And then you run the first calculation of Hubbard U and V using density functional perturbation theory, DFPT, or linear response theory that I described before. So this way you get Hubbard U and V parameters, but then you check if these Hubbard U and V and structure are converged. That is to say, you compare the ones that you obtain with previous ones. Of course, since we start with U and V 0, and now we got U and V are some, let's say, numbers, of course, the difference will be huge. And the same for the structure. So we say no, the self-consistency is not achieved. We go back. And now we use this U and V as an update. And now we perform structural optimization with this U and V that we just computed. Then you do SCF ground state with U and V that we just computed. And then you recalculate U and V. And you obtain slightly different U and V. Now we check the updated U and V. Is it still different from the previous one? And typically, yes. You need to repeat the cycle 3 to 4 times typically. And when you compare U and V, you need to set a threshold. Let's say how much you want the U and V to be stabilized. Typically, we take 0.1 electron volt or 0.01 electron volt. And once you reach the convergence, you exit the loop. You go to the green rectangle. You say we reached the self-consistency. Hubbard U is self-consistent, V is self-consistent, and geometry is optimized. So that's what we typically do. We optimize geometry and calculate U and V self-consistently. So it's called self-consistent workflow. And to make it work, we need to perform structural optimization, which needs Hubbard contributions to the forces and stresses, which I will not cover because it's the entire discussion. And then we calculate U and V as we presented before using linear response theory. Just to give you an example on the right, for this other battery material, lithium manganese phosphorus 4, just to show you how Hubbard U changes and V changes during this self-consistency. Let's take just the top panel, which is the DFT plus U framework. Hubbard U is a function of iterations. So the first iteration in this loop on the left, you get Hubbard U slightly higher than 5 eV. Then you do the second loop, it goes down to 4.2 eV. We see a change from 5.1 to 4.2. It's a big change. Then you do the third step, third iteration. The change is smaller now, just changed by 0.2 eV or so. And then the last step, it almost doesn't change. So you see, it's kind of, there is a big variation at the beginning, but then it stabilizes. It means we're getting the self-consistency. And same for the V. At the beginning, there is a little bit of variation, but then it stabilizes pretty quickly. And the V parameter is below 1 eV typically, or around 1 electron volt. So it's much smaller than the Hubbard U. So that was all about the method. And we have many applications of DFT plus U and DFT plus U plus V. This is just like a tree of applications. I would like to mention that lithium-ion batteries, phonons, you can also use Hubbard U correction in phonons. You can study defect physics in perovskites. You can study photocatalytic water splitting, muon spectroscopy, electron-phonon coupling, magnons, and so on and so forth. So fortunately, I don't have time to talk about applications. It's also very interesting, but maybe another time. But that's all for today. In the remaining 10 minutes, I will discuss a little bit about the hands-on, but maybe you have some questions about the lecture. That's the opportunity to ask your final questions about the DFT plus U method and the whole lecture, 3-hour lecture in total. Please ask now if you have any questions. Okay, if not, then I can maybe briefly introduce the hands-on. Okay, so the hands-on today can be done using this material from the mini assessment school that we ran in June this year in Ghana. In this school, it was a two-week school in person. We covered different topics similar to the topics of this school, like DFT, DFT plus U, and phonons, and so on. So there is a specific exercises for DFT plus U. So let me put this in the chat so you can have the access to this web page. There are two exercises. Exercise 1 for cobalt oxide and exercise 2 about iron oxide. So there is a PDF document here. It's called Day 1 Hands-On. You can click on the PDF and it describes what to do, like step by step, an introduction, and what to do. Okay. So here in exercise 1, you have all the files, input files, README. So README tells you how to run it on your laptops. And there is even references, tar, GZ. You can uncompress and check the outputs. And same for the exercise 2. Again, you have input files and how to run the hands-on. So yes, that's it. Basically, you have two examples, cobalt oxide and iron oxide. The one that we mentioned during the lecture. So I think you should enjoy it. Then I would like also to share with you a link to another material online. That was another tutorial already several years ago. Here there is first of all, let me put it in the chat. It's from another school. So why I'm sharing this? Because there is video recording. So if you go to day 2, there is this hands-on, 2 hands-ons, and there are slides and video. So if you click on video, you can see the video recording of the hands-on. So it's similar to what you have now. So you can just press and watch basically my comments on how to analyze the hands-on and how to run it. And finally, also in June this year, there was a joint ICTP Marvel College in Italy. And there we also presented lecture and hands-on. So let me put it in the chat. So there is a lot of other very useful material here. There are video recordings. If you go to program, there are many lectures, also including machine learning and DFT and everything. So there are, I see, slides and video. So I highly recommend you to watch all of this. In particular, for DFT plus U, here we have, again, slides and video of Professor Matteo Coccocioni and myself, slides and video. So it's similar to my lecture here. And there is also hands-on video recording, so that could be also useful. So again, this is another useful material for you if you are interested in more in DFT plus U. Okay, that's it for what I wanted to cover today. We have still some time to answer questions, if you have any, about hands-on, about lecture, about today's topic in general. Are there any questions?
For the participant, you can also write your question.
Can wait a little moment, maybe someone can come up with some questions. If not, then thank you so much.
Mm.
It was my pleasure. Okay,
There is
something.
yes, a question. I got lost during the part of calculation. Would you please explain it again? Which part of the calculations? The tutorials?
Okay. Yes. So I shared a lot of material. So the one you need is this one, mini assessment. So this link. So I posted in the chat 3 links. So you should use the first link, GitHub mini assessment 2026. So this is what you have to do. The other 2 links are useful because there are video recordings. So if you don't understand how to do it, you can check those.
Okay, today we will have the tutorial at 4 and we will follow this tutorial
Perfect. Thank you so
in
much.
the mini assessment. And to get more understanding of it, there is 2 also suggested links to watch the videos and get the steps more clear.
Thank you. Now, how to download this tutorial? So you need to click on mini assessment to go here, and then there is this green button code. You click on it, and then you can download it. So one way to download it, so you can click download zip here, or if you're familiar with SSH, you can just copy URL to clipboard, copy, and then you open a terminal. So I go to desktop, and then you type git clone, and you insert the link. So you type git clone the link to the material. Then you press enter. It downloads locally the folder. Okay. You see, now I have mini assessment 2026. And here there is week 1 and week 2. So you need to go to week 2. Week 2, day 1. Okay, this is the, let me see if it works. No, actually it's not. Yeah, if I look at it like this, so week 2, day 1, this is the hands-on. You see there are slides. You can go through slides. It explains how to run it, what is the input file, all this. It's without comments. So there are video recordings with comments. That's why I recommend you to go through it. How to compute Hubbard U using the HP code. And iron oxide, it's a bit trickier how to work with it. Yeah, it's all, yeah, if you can check video recordings, it all explains how to do it. Yes. Thank you too.
Okay. If there is no questions now, thank you so much, Dr. Iurii, for the nice lecture, and thank you so much. For the participant, we will have the tutorial at 4 today. So thank you for everyone, and yeah. Goodbye.
Thank you so much. Thank you.
Someone was asking?
No, it was just saying thank you, I think.
Okay, thank you. Okay,
All right.
bye.
Thank you. Enjoy the rest of the school.
Thank you.
Best of luck. Bye-bye.
Bye.
Bye, teacher.
Bye-bye.